I'm going to talk about superplasticity. This is continuation of yesterday's lecture. I'm Dr. Narayanasamy, retired professor from National Institute of Technology, Tiruchirappalli. This is the typical tensile test. It is plotted between, this graph is plotted between logarithmic of log sigma, that is true stress, and log strain rate epsilon dot. This is nothing but sigmoidal curve. The variation of the flow stress with the strain rate is nothing but sigmoidal curve. This is stage 1. Up to this point, this is stage 1. This is stage 2. This is stage 3. In the stage 1, there is no superplasticity. The stage 2, maximum strain rate sensitivity can be obtained. So this is the region where superplastic deformation is possible. This is the region where superplasticity will be slowly lost. Next. This is the shape of the deforming specimen sample. When n is dominant, say n is 0.3, m is 0, m equal to 0, strain gardening is dominant, so deformation is restricted here. Deformation is not much. When n is 0, m is dominant, say m is equal to 0.5, n is equal to 0, very large deformation is possible because of diffuse necking. Extreme elongation is possible. Then we talk about plastic instability. At the onset of necking, when m equal to 0, the plastic instability can be written as sigma plus d sigma into a into d sigma is greater than or equal to sigma into a, where d sigma and d are the incremental change in stress instantaneous cross-sectional area. Neglecting the second order terms, we get d sigma by sigma is greater than or equal to minus dA by dA. For constant volume principle, minus dA by A equal to dL by L equal to d epsilon. So this can be written as d sigma by sigma equal to greater than or equal to minus d by A equal to dL by L equal to d epsilon. So d sigma by sigma is greater than or equal to d sigma. For stability, d sigma by d epsilon should be greater than or equal to sigma. For this is instability condition. For instability condition, epsilon equal to n value. At the maximum load point, it will take place. For Newtonian viscous flow, n equal to 0, strain gardening exponent is 0, strain rate sensitivity m equal to 1. Epsilon dot is given by d epsilon by dt. This is equal to a minus 1 over a into dA by dt. This is equal to 1 over L into dL by dt equal to dA by dt. This can be written as the epsilon dot is written as a into epsilon dot. So minus dA by dt equal to a into epsilon dot. This is epsilon a equal to sigma by k from constitutive equation sigma by k. This is a into sigma is nothing but p. So dA by dt equal to p by k minus dA by dt equal to p by k, where p is equal to sigma into a. For plastic instability, for this material, for superplastic material, the rate of loss of area at any cross-section is dependent only on the load, and it is independent of the cross-sectional area. This is as the time increases, when the time is 0, for example, when the time is 0, let us say the specimen is something like this, no necking, slowly the neck formation is delayed process. It's a delayed process. For plastic instability, d sigma is given by d sigma by d epsilon into d epsilon plus partial derivative of sigma with respect to strain rate into d epsilon dot. For flow stable For stable flow, d epsilon sigma del A dot by del A should be less than or equal to 0. This can be written as d sigma by partial derivative stress with respect to strain plus epsilon dot into partial derivative stress with the strain rate is greater than or equal to sigma. So n by epsilon equal to plus n by epsilon plus m is greater than or equal to 1. For plastic instability, for m, when m is greater than 0.5, there is no necking. There is no necking. For superplastic material, m varies from 0.3 to 0.9. N is square 0. Strain gathering exponent is 0. M strain rate sensitivity is greater than 0.5. We know that P is given by sigma into A. So this can be written as epsilon dot is given by minus 1 over A into dA by dt. This can be written as sigma by k power 1 power m. dA by dt equal to minus p by k 1 power m into 1 divided by a power 1 minus m divided by m. When m increases from 0.3 to 0.9, 1 minus m divided by m decreases from 2.33 to 2.1. When m equal to 1, the dependence of dA by dt on A decreases. The extreme elongation is possible. Extreme elongation for superplastic material is possible. This is due to the result of very high resistance to neck growth. Plastic instability, geometry of dike formation. This is type A, this is type 2. Type A, in the case of type A, it involves formation of several necks during uniform deformation. This is one neck, this is one neck, this is second neck. This is one neck, second neck, third neck. So during deformation, several necks are active during the uniform deformation. When the number of active necks are growing concurrently, one becomes dominant, which grows to failure, produce failure. There are so many necks. One of the neck may be dominant, finally leads to failure in this case. For superplastic deformation, extreme elongation is possible. Elongation in the order of several hundred to few thousand is possible. Percentage elongation can be determined using this expression. When beta equal to 0, in this case, because rupture takes place in the smallest area of cross section, percentage elongation is given by L0 plus L plus 100 into 1 minus alpha 1 power 1 minus m 1 by m power minus m minus 1, where alpha is a constant and m is strain rate sensitivity. For superplastic deformation, extreme elongation is possible. This plot is made between logarithmic elongation, logarithmic value of elongation and strain rate sensitivity. As the strain rate sensitivity increases, the elongation percentage also increases. Or this plot is made between logarithmic m value versus logarithmic elongation. So as the elongation increases, m also increases with increasing elongation. This is plastic instability. The strain rate sensitivity index m is given by d of epsilon sigma divided by d of epsilon dot. The slope of ln of sigma versus ln of epsilon curve, where m is the strain rate sensitivity. This is done between m and logarithmic strain rate. Here the m value increases, reaches the maximum value and then drops. Here the m value is very low, so superplasticity is not possible. In this strain rate range, superplasticity is possible. Superplasticity is taking place in this region. In this region, superplasticity is being lost. M value can be determined using this expression. Strain rate sensitivity m can be determined by this equation. This plot is made between load versus time. We change from one velocity to another velocity, v1 to v2. So let us say at V1, PB is the load value. When you change to V2, the load value is P2, PA. So M is given by ln of PA by PB divided by ln of VA by VB, or M equal to ln of sigma A by sigma C divided by ln of epsilon dot A epsilon dot C. So this is given by 1 over M equal to d ln of sigma divided sigma dot divided by d ln of sigma. So ln of sigma is given by C plus M divided by 1 minus M into ln of T plus N. Where C and D are constant, slope ln of T versus ln of should yield straight line graph, which is M divided by M minus 1. This stress relation test yield more satisfactory fundamental data because of very small strain. The significance of M value is given here. There is a disagreement in this value by various methods due to necking, differential defect, structure because of various strain involved, wide variation in M value over the strain rate, grain growth. Because of grain growth, M value will be affected. The sign and magnitude of the strain rate also change is involved. The properties of various alloys. Various alloys that can be superplastically deformed is given here. Titanium 6 aluminum 4 vanadium. ML is 0.85. Percentage Langan is 1000. Ti 5L 2.5N. Here ML is 0.72. Percentage Langan is 450. Ti 8 manganese. ML is 0.5. Percentage Langan is 450. Like this, various alloys M value and percentage manganese is reported. This case, titanium has application in aerospace industries. Application of various alloys. Titanium alloys. These are titanium alloys has various applications, particularly in aerospace industries, aircraft engines, jet engine compressor, aircraft turbine compressor, aircraft structural parts, aircraft sheet metal component, aircraft hydraulic component. One second. Solve. ఏం చేయాలా అర్థ రాడా రాడా ఇది అవసరం మెల్ల చెయ్యి అవసరపడగా ఇది పెట్టుకో పక్కన వచ్చి